Alright guys, let's see how we can solve question 53 from the first chapter of the Beer and Johnson textbook, Mechanics of Materials. And we have two vertical links, CF, connecting the two horizontal members AD and EG that has a 10 by 40 millimeter uniform rectangular cross section. So the question is referring to these two links of CF. We have one at the front and one in the back that connects the two links of AG and AD. So we have the dimensions for the link CF, it's 10 by 40 and it's made of steel. And we know that the ultimate strength in tension is 40 megapascal. So we know that the link CF is made of steel, and we also have the ultimate tension, 400 megapascal. And each of the pins at point C and F has a 20 millimeter diameter. So we have two pins, one at point C, one at point F, which has the diameter of 20 millimeter. So those pins are made of steel as well. And we have the ultimate shear stress in those two, which is 150 megapascal. And we need to determine the overall factor of safety for the link CF and the pins connecting them to the horizontal member. So we're dealing with two different things. We have the shear in the pin that might fail the system, and we also have the link by itself. They're both made of steel, but they have different ultimate stress. And from the question, since we have the ultimate strength in tension for CF, looks like that the link CF is actually in tension. But let's see how we can figure that out. That is actually in tension. So we're going to start with the free body diagram of the bottom part, or the member, or the rod EG. So if we just draw the free body diagram for that, so this would be the free body diagram of EG. So we're going to have the force 24 kilonewtons at point G. We have the tension in the link. We can show it with this. We're just going to assume one direction for now, and this would be the force that is applying from the link to the joint F. So we're going to call it FCF. We can just assume one direction for now, and we'll figure it out based on our equilibrium equations. So we assume that the system is in equilibrium. So we're going to use those equations that we have, and let's just assume one other force in here, FEB, in this direction. For now, we'll figure out if the direction is correct or not. So what we are interested in here is the factor of safety in link CF. So if you're looking for factor of safety in CF, which would be the ultimate force CF over the actual force that is applying at CF. So we are interested in this force FCF ultimately in this question. And as I mentioned, we are in equilibrium, or we assume that we are in equilibrium. And when we are in equilibrium, we have sum of all forces equals 0, and we have the same for moment. We have two unknowns. It seems that if we do our moment equation about point E, so this is E, this is F, and this will be G, we can get rid of the unknown at point E, which is the force in EB. So we should be able to find the FCF in here, and we're going to call counterclockwise positive as always. So we have the moment of the FCF, which if we look at it, it will be in this direction. So we have a counterclockwise moment. So positive FCF times the distance from E to the line of action, which is what we have in here. That's going to be 400 millimeter. So times 400. And we don't need to do unit conversion. I'm going to explain shortly. So the other moment that we have is the moment of 24 kilonewton. This one is clockwise, so it will be negative moment. So minus 24 times the distance from E to the line of action, which would be basically the distance from E to G, or we have 215 here. So we have all the distances in the figure. 400 plus 250 equals 0. The reason I didn't do unit conversion was that because we have this 1 millimeter and this will be millimeter too. If we divide them by 1,000 in order to get it in meter, it will be canceled out anyway in here. So that's why I didn't do the unit conversion. So our FCF here would be 24 times 400 plus 250, 650 divided by 400. So let's calculate this. That's going to give us the force in kilonewton. So 24 times 650 divided by 400. So this is going to be 39 kilonewtons as the force FCF. So we found the denominator in here, but for the numerator, we have the ultimate force in here. One thing I forgot to mention in here is that the FCF that we have in here, it's going to be the resultant of the force from each of these two links. So we have two links in here, which each of them has the force. So the FCF that we have in here would be actually the resultant of these two, or the net force from the two links. The other thing that we could do is that if we want to go with each single link, we can just put a 2 in here. But let's just keep it like that for now. But keep in mind that the area that we're going to choose later for finding the stress will be a bit affected by this. And also one other thing, at the end of this, we did not get any negative sign. That shows that our assumption was actually correct. And this is the correct direction for FCF, which again, as I said, is the force from the link to the joint. So if we look at the joint, if we look at the member CF in here, which is this member, the force from the joint to the member has to be in the opposite direction, which will be downward, based on Newton's law. So if we look at this, we'll see that the member in here is actually in tension, and that's why the question is giving us the ultimate stress in tension 400. So now we know that the link CF is actually in tension. So let's start with that. We have based on tension in link CF, we're gonna have the ultimate tension stress, which will be the ultimate force in CF over the area. And we already know that this is equal to 400 megapascal, which is the given in the question. But what we need to figure out in here is the area. And let's see what area that we are dealing with. So as I said, the FCF would be the resultant of the two links that we have at CF. So the link CF that we have, so obviously we have one at the front and one in the back. So the area that we need to consider in here would be this area. So we discussed this in the previous question in the channel. So when we are talking about when we have a member in tension, where the failure happen would be the location of the failure would be where we have the holes located or where the pin is located. So the area that we are dealing for that stress would be the area of this shaded area, which is what we have in here. So if we do a cross section in here, what we're going to see is this one. And obviously, as I mentioned, we have two links, one at the front and one at the back. So there will be one more in the back too. So the area that we are looking for would be this area. And for this, we need all the dimensions. If we look at the question, it says that the dimension of the link is 10 by 40 millimeter. So this will be 40 and the thickness would be 10. We also have the diameter of the pin in the question, which was what we have in here. 20 millimeter diameter is what we have here. So now we have to figure out the area of the shaded parts in these links. So we can do for one, and I just do times 2. So if you want to find one of them, we have, so basically we are dealing with this rectangle area. So one side is 40, the other side is 10. So we're gonna have, we can show it either 40 times 10 minus, and also we know this is 20 times 10, or we can just factor 10 in here, which will be 40 minus 20. So that's going to be the area that we are dealing with. So it's going to be 400 millimeters squared, or if you want to have it in meters squared, it's going to be 400 times 10 to the minus 6. So now it's easy if you just cross multiply these two. we can find the ultimate force in CF, which will be 400 megapascal or 10 to the 6 Pascal times 400 times 10 to the minus 6. So these two will be cancelled out, and we're going to get the force in newtons, which will be 16, 1, 2, 3, 4 newtons, or 160 kilonewtons. So we can find one factor of safety based on this ultimate force if we get back to our formula at the beginning. So we were trying to figure this out. So we can get one factor of safety in here. So based on the tension in the link, we're going to get 160 over the force was 39. Let's see what we get. 160 divided by 39, that's going to give us 4.1. And that would be our first factor of safety based on the tension in the link. But that's one part of the story. The other part of the story is the shear stress that each pin is tolerating. So now we're going to go based on the shear stress on pins. So now we have the ultimate shear stress, again, the ultimate force in CF over the area. Let's show it with A prime just to differentiate with the previous one. So the area now, it would be the area of this. So we have that pin, which is going up with the force that is applying. So the area that the pin is gonna experience the shear stress would be these two areas, and we have the diameter, same thing, 20 millimeter would be the diameter of each pin. So the area would be pi over 4 times the diameter 20 millimeter squared. And since we have two of these, so we're going to multiply it by 2. Because again, this FCF that we introduce in here would be applied. I said that it will be the resultant of the two links. So the area that are engaged in here are in both sides of the pin, at two sides in the pin. So we have these two areas, and the rest is pretty similar. And we know that the ultimate shear stress, if we get back to the question, is 150 megapascal. So this is 150 megapascal. So that's going to be times 150. So if we just, again, cross multiply these, we can find the ultimate force in CF based on the shear stress on pins. So 150 times 10 to the 6, because it's megapascal, times pi over 4 times 20 squared would be 400 times 2, 800. And this can be canceled out with this. So 150 times pi times 200. Now also I forgot 10 to the minus 6 in here in order to make it in meters squared. So here we have 10 to the minus 6. So that's going to give us 94,247.8. Or if you want to just report it in kilonewton, it's going to be 94.25 kilonewtons. So we can find another factor of safety here. So 94.25 divided by the FCF that we found from our free body diagram, 39. So let's divide that by 39. And it's going to divide by 1,002. That's going to give us 2.42 as the second factor of safety. So now we have two factor of safety, one based on the tension in the link, one based on the shear on pin. And here we're going to pick the lower one, as we discussed in the previous question. The component that has the lower factor of safety is more vulnerable to failure, so it will compromise the system. And that's why the final answer for this question would be 2.42, and we're going to go with this factor of safety. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next one.